Let me jump into it. So first of all, why do we want to care about embedding stability? You might argue that since embeddings are a internal abstraction of a model, we might only care about things like downstream prediction accuracy. But the key is for the reason that we care about this is because embeddings are very useful for downstream applications. They provide a nice encapsulation of everything that a model learns about users and items. And then those end up being very useful representations for downstream models. But because embeddings are this sort of arbitrary internal representation, there is an issue with trying to use them in downstream applications, which is that between model training cycles, the embedding space has this arbitrary degree of freedom such that you can't interchangeably use embeddings from different training runs. And so in the best case, this causes issues where you have to frequently retrain downstream models. Worst case, it can cause things to break as you switch from one model deployment to another. So what we would like to address is provide a way to stabilize embeddings without sacrificing our model quality or adding some additional heavy overhead or requirements. So that will be the focus of this talk. First, to ground in the problem setting, this will apply to anything that is sort of a factorization style recommender model where we produce scores as a dot product between users and items. So I'll refer to T and W as low dimensional matrices of item and user representations respectively, where these can come from any arbitrary function, for example, two-tower model or anything else, as long as we can define a score for users and items as the product of user and item embeddings. And there's two reasons that embeddings might change. One, due to model prediction drift, where the scores are actually changing, and two, this degeneracy, this arbitrary degree of freedom from the orientation of the latent space. So in this work, we address the second of these two factors in order to remove that arbitrary degeneracy to stabilize the embedding space. So as a simple illustration to motivate this, consider two model runs with identical scores. Ideally, we would like it to be the case that if the scores are identical, the user and item representations are identical. However, that is not generally the case, and there can be an arbitrary mapping between the learned users and items. And so downstream consumers can't rely on any meaning of a particular dimension in the embedding space or the stability of those embeddings. So we're going to try to address this. And our approach has two steps. The first step is we're going to compute a canonical low-rank factorization of the score matrix. And the second step is that we're going to align our models to a reference embedding space using an orthonormal transformation. And I'll claim that this approach is fast and lightweight with no requirements for retraining your model or implications for additional changes to the structure of the model. It exactly preserves the dot product between users and items, so no information is lost, and it has a nice mathematical interpretation. So the first step is that we're going to do a singular value decomposition. But doing a direct SVD on the score matrix is infeasible because this score matrix can be hundreds of millions of users, many, many items. You don't want to compute the whole thing, let alone compute an SVD on it. But what we can take advantage of is the fact that we already have a low-rank decomposition, even if it's not the low-rank decomposition that we want, which is whatever the model learns for these low-dimensional user and item representations. So doing a little bit of linear algebra, we can take a QR decomposition of the user and item representations, which we can do at scale with Spark. And then we only need to compute SVD on a small matrix with embedding of the size of the embedding dimensionality, which we can do very easily. And this gives us transformation matrices that we can apply to the user and item embeddings that preserve the score. So then, given that we have this canonical SVD representation, the next thing that we need to do is align as best we can to some previous standardized space. So we'll do this using the well-understood technique of orthogonal Procrustes, where we will learn an orthogonal matrix R that best maps the one embedding space to a previous selected standardized run. And this is something that we can compute efficiently, and it has nice numerical stability. So putting those two things together, we're going to start by picking a reference model run. Then we're going to put it into a canonical SVD-defined embedding space. And then for each new subsequent run, we will put that embedding space into this canonical form and then align to the standard reference space. So in practice, this is something we can do as a lightweight post-processing step to our existing model. At the end, we just have a small D by D matrix multiplication that you could insert, say, as a final layer of a neural network, or apply as matrix multiplication in a Spark job. This is easily applied to either batch or online inference pipelines without affecting the model architecture itself. So how to evaluate this? First of all, we know by construction that within a single run, the user and item embeddings still produce consistent scores. So in a Hippocratic sense, we first do no harm. You're not going to lose out on anything by applying this. But we additionally want this to do well for stabilizing embeddings across different retraining runs. So to look at this, we'll compare cosine similarity of user and items across different days and correlation of user and item scores, and see that without stabilization, these scores are essentially uncorrelated, but with stabilization, we'll get much higher alignment. So we've applied this in our internal recommender model and have this running in production. I show here for 3 periods separated by a sequence of 2 weeks each. We can see that the correlation between user and item cosine similarities, as well as a rank correlation using user and item products across different days, produces useful, meaningful correlation as opposed to random noise. So in conclusion, this is a method that we can use to stabilize embedding spaces across retraining cycles, preserving dot products and inference quality. It's lightweight, scalable, and easy to integrate, and it enables our downstream applications to use these embeddings without worrying as much about what happens when a new model training run is deployed. So, thank you.
Your method aims to stabilize embeddings across retrains, which sounds very useful, but how do you make sure that the stability doesn't come at the cost of missing genuine shifts in user behavior or item dynamics?
Sure, yeah. I mean, so missing shifts, I mean, first of all, like, you're not losing out on anything by doing this, right? So, like, because you're preserving the dot product of the user item scores, if there is a shift in the sort of underlying distribution, the worst thing that will do is that your like canonical SVD space differs from what you would compute on a fresh retraining run, but that doesn't actually like cost you anything in terms of the representation quality. So I would say that there's not any impact to representation quality, and the sort of training run drift of like the underlying scores is, yeah, there's a natural process, but I'd say if that's the thing that you're worried about, you could try to address it by other means, but that's not like that's sort of outside of the scope of this, and something that I don't think negatively interferes with it.
Yeah, thank you for your presentation, and I think my question is pretty similar to the one that was asked already, but I'll still ask it in case maybe there's a slightly different answer. But yeah, does this approach actually limit the capabilities of the model, of the whole process to learn from new interactions. So, for example, when you retrain, you have new interactions like that. Is that limited?
Yeah, no, there's no limitation on the model, right? Because we preserve the model scores. So whatever the model is, like the embeddings are just this underlying abstraction, like with internal to the model. It's got this open degree of freedom of like you can apply some. As long as you apply some orthogonal transformation to users and then the transpose of that to items, you get something where the product of those is unchanged, right? So because you're doing this as a post-processing step, there's no constraint on the model's ability to learn from new interactions.
So here, Lucas says, given that SVD tends to emphasize dominant components, how do you prevent rare or low variance signals from being lost in the projection, especially for call start or tail entities?
Yeah, sure. I mean, I think this is, I guess I still want to like emphasize the point that there's no change to the scores. So we're not like harming any predictions for, if you, yes, like the first component of the SVD is going to like correlate strongly to popularity, but like that's something that, is maybe useful as an interpretability dimension. It's not something that is affecting the quality of the predictions. So there's not any harm to like low unpopular items from this.
Thanks for the presentation. So probably aligned with the previous questions. We don't do the full SVD. We do an approximation of that. And probably the model drifts slowly over the time. Have you studied what is the drifting speed and when it's better to stop and do the full retraining, or in general, how to behave in this case, since we are switching to the continuous model of the same SVD model matrices?
Yeah, this is an interesting question, and I think like gets at a lot of the interesting approaches of like how do you want to think about like model retraining, warm starting versus like full retraining of a model. I would say like you can use this approach to look at drift of items and users over time. I think it's even more useful like if you are combining this with like a warm start continual retraining, because that like gives you a certain amount of stability. This approach like layers nicely with other things that might improve the stability of your representations. So if you're doing something like a warm start approach, you still have that like degree of freedom within the model. So you might get additional drift beyond just like what's necessary to update the representations. And then like if you apply a stabilization on top of that, I think you can get a cleaner view of how the actual like content drift is happening over time. And you can look at that for your specific application and see like, if that gives you something useful to help assess retraining cycles. But I would say that like I would mostly think about retraining, like fresh retraining versus warm start, from the perspective of how does that affect your like your actual application rather than how it affects the embeddings.